So I'm holding this document you sent over for today's deep dive. And I have to admit, my first reaction was a bit of nostalgia mixed with, well, let's call it minor academic trauma.
Trauma. That's a strong start. What exactly are we looking at here?
It's a chemistry text, the chemistry of pure substances and mixtures. And it looks like standard curriculum stuff, definitions, diagrams of beakers, bolded vocabulary words. But then I started reading the margins.
Right.
And that's where the real show is.
Because we aren't just reading a textbook today. We're reading a textbook that's been aggressively fact-checked and occasionally roasted by a student named Aram.
Aram is essentially the uninvited third host of this deep dive. And honestly, he's asking the questions I was way too afraid to ask in 11th grade. He's lighting matches in his kitchen, he's putting magnets in his cereal, and he has some very strong opinions about the geopolitical implications of the word oil.
He's applying the scientific method in its most chaotic form. I mean, usually when we look at scientific texts, they are polished, sterile. They present facts as these immutable laws from on high.
Yeah, exactly.
But Aram is in the margins poking the world with a stick to see if it explodes.
Now, I do want to make a quick disclaimer for you listening at home.
Yeah.
The source material we are working with today, it's a little rough around the edges.
That's putting it mildly.
Yeah, there are some typos in the original text, some grammar quirks, some weird spelling choices from our guy Aram. But our main focus today is to just ignore typos, please. Like, seriously ignore the typos.
Right.
We are just going to look right past them.
Because we aren't here to grade the grammar. We are here for the science, which is actually quite solid, and more importantly, for that spirit of inquiry.
Exactly.
It's a reminder that science isn't just about memorizing that H2O is water. It's about the texture of reality.
So our mission today is twofold. First, we're going to master the fundamental makeup of the world around us. We need to distinguish between what is pure and what is a mixture.
Essential stuff.
Right. And second, we are going to learn the toolkit of separation. Because if you have a bucket of sludge or a bowl of cereal or a barrel of crude oil, how do you get the good stuff out?
It's the ultimate survival skill, really. Separation is how we get clean water, how we get fuel, how we get food. It is the act of creating order out of entropy.
And along the way, we're going to follow Aram's advice on what not to drink and why he thinks petroleum jelly is a conspiracy to put fuel on your face.
I cannot wait to unpack that one.
Okay, let's dive in. Section 1, the building blocks. We have to start with this word, pure.
Pure. It sounds simple, right? I mean, in our normal lives, pure is a marketing term. Pure orange juice. Pure wool. Pure intentions.
Right.
It implies goodness. It implies quality.
If I buy pure honey, I expect it to not be corn syrup. I expect it to just be honey.
Exactly. But in chemistry, pure is a rigid, almost totalitarian definition. A pure substance is made up of only one kind of particle. It is uniform all the way down to the atomic level.
So if I go to a mountain spring, pristine nature, and scoop up some crystal clear water, is that a pure substance?
Chemically, no, absolutely not. That is a mixture.
Really?
Yeah, it has dissolved minerals, salts, maybe some dissolved oxygen, some bacteria. To a chemist, that water is dirty not in a hygiene sense, but in a compositional sense.
Wow, okay.
In the lab, a pure substance has fixed chemical properties and a fixed ratio of elements. Water is only a pure substance if it is 100% H2O and absolutely nothing else.
And this brings us to our first intervention from Aram. The text mentions water prepared in the laboratory, and Aram has scribbled a giant, frantic warning next to this.
He has. Let me read it. He writes, by prepared in the lab, it means distilled water with NO minerals, aka pure water, and do not drink it as human bodies want the minerals in the water and will not accept pure water.
Is he being dramatic here? Because I see distilled water sold in grocery stores right next to the ironing boards. I've always assumed it was just extra clean water.
He's being dramatic, but he's actually spot on regarding the biological mechanism. It's not that the water is poisonous like arsenic. It's that it's aggressive.
Aggressive how? It's water. How can water be aggressive?
It's about osmosis. Your cells are salty. They are little bags of water, salt, potassium, and sugar. Nature always wants balance.
Right.
So if you flood your system with 100% pure deionized water, water with zero dissolved solids, what happens?
I think I remember this from high school biology. The water wants to go where the salt is.
Bingo. The water rushes into your cells to try and dilute that salt. It can cause your cells to swell.
Oh, wow.
At the same time, because there are no minerals in the water to balance the minerals in your blood, the water acts like a magnet leaching electrolytes out of your tissues.
So you're drinking water, but you're essentially washing the electrical conductivity out of your nervous system.
In extreme cases, yes.
Right.
It's called hyponatremia. Ahriman puts it simply, the body will not accept pure water, and he's right. We evolved to drink river water, spring water, mixtures. We are built for dirty water, chemically speaking.
That is such a crucial distinction. We constantly equate purity with health, but biology actually requires the mixture.
Precisely. Now, within this category of pure substances, the stuff that will kill you if you drink too much of it. The text breaks it down into two subcategories, elements and compounds.
Let's run through those. Elements seem pretty straightforward, the periodic table stuff.
Right. Elements are the raw building blocks. Iron, silver, gold, sodium. You can't break gold down into anything other than gold atoms using chemical means. It just is what it is.
But then we have compounds. And this is where I feel like the distinction gets a little blurry for people. The text says compounds are pure substances made of two or more elements. But if it's two things, why isn't it a mixture?
That is the million-dollar question. The difference is the GOND. In a compound, the elements have chemically fused to create a completely new identity.
Give me an example of that.
Take sodium and chlorine. Sodium is a soft metal that literally explodes if you touch it to water.
Bad.
Chlorine is a deadly green gas that was used as a chemical weapon in World War I.
Okay, so two very bad things. Very dangerous.
Exactly. But if you mix them together chemically, they bond to form sodium chloride, table salt, something you sprinkle on your eggs every morning.
That's wild. The properties completely flip.
That's a compound, a new identity. The ratio is fixed 1 sodium, 1 chlorine. If you just tossed sodium chunks into a jar of chlorine gas without them reacting, that would be a mixture, and a very dangerous one.
Aram notes here that compounds can also be called molecules, which is a good catch. We can ignore the slightly weird spelling he used there and just appreciate the science.
It is a good catch. So that's the pure side of the room. It's strict, it's organized, it's fixed. But then we step out into the real world and we encounter mixtures.
The text gets almost poetic here, actually. It says, the ground that you stand on, the air that you breathe, and the oceans of the earth are all mixtures.
And it's true. Purity is rare in nature. It takes immense energy to purify things. Nature favors entropy, the mixing of things. The defining characteristic of a mixture is that the components retain their own properties.
Retain their own properties. Let's unpack that a bit.
Think about salt water again. That's a mixture. You have water and you have salt. If you mix them, the water is still wet and the salt is still salty. You haven't created a new chemical bond, you've just jumbled them together.
Okay.
If you evaporate the water, the salt is left behind exactly as it was before. It didn't turn into a new magic crystal. It's just salt that got wet.
The text gives some great everyday examples. Milk, for one.
Milk is a fascinating one because it looks pure. It looks like a uniform white liquid. But under a microscope, it's absolute chaos. It's water fats, proteins, and sugars all just suspended together.
And brass. That one actually surprised me. Brass is a solid hard metal. How is that a mixture? I'm looking at a brass doorknob in my house, and it looks uniform. It feels like a single material. It doesn't look like a mixture of anything.
This is where the definition of mixture gets really cool. It's not just about things you can stir with a spoon. Brass is what we call a solid solution.
A solid solution. How does that work?
Imagine a perfect stack of oranges in a grocery store. That's a crystal lattice of pure copper. All the atoms are the exact same size lined up perfectly. Now, if you push on that stack, the layers slide over each other easily. That's why pure copper is soft and bendable.
Okay, so how do we get brass out of that?
You melt the copper and you throw in zinc. Zinc atoms are a completely different size. When the metal cools and refreezes, those zinc atoms get stuck in the lattice. They're like tennis balls shoved into that stack of oranges.
They ruin the perfect stacking.
Exactly. They act as roadblocks. Now, when you try to bend the metal, the layers can't slide because these awkward zinc atoms are locking everything in place. That's why brass is much harder than pure copper.
So it's a mixture, but the mixing happens at the atomic level to engineer the physical properties.
Precisely. It's an atomic traffic jam, and that's what makes it useful, but chemically. The copper is still copper, and the zinc is still zinc. You could theoretically separate them back out.
Okay, so we have established that most of reality is a mixture. But not all mixtures look the same. This leads us to section 2. The texture of reality. Homogeneous versus heterogeneous.
These are big words for a very simple concept. Does it look the same throughout, or is it chunky?
Chunky, is that the technical term we're going with today?
Well, scientifically, we'd say macroscopically non-uniform, but chunky paints the picture better. A homogeneous mixture is uniform. You can't see the different parts. The classic example is sugar dissolved in water.
The text says, the first sip is as sweet as the last sip.
Right, because the sugar molecules are evenly distributed throughout the water. But Aram takes issue with this.
I love this note so much. Aram writes, but if you put too much sugar in the water, like I like sugar water, it will get super saturated, and then the last sips might have some sugar left over, so more sweet. Pun not intended.
This is brilliant because he's actually anticipating a concept that comes later in the chapter, saturation. He knows from personal experience, probably from making incredibly unhealthy sugar sludge in his kitchen, that there is a limit.
He's pointing out the boundary condition of the rule.
Exactly. If you exceed the solubility limit, the sugar stops dissolving and just sits at the bottom. In that case, it stops being a homogeneous mixture and becomes heterogeneous because you can clearly see the pile of sugar at the bottom of the glass. So Aram has technically debugged the textbook example. He's saying this is only true up to a point.
Now let's talk about heterogeneous mixtures, the non-uniform ones.
This is where you can clearly see the different parts. Sand in water is the classic example. You stir it up, it looks cloudy, but eventually the sand settles.
This is where Aram gets really critical of the text's analogies. The text tries to explain non-uniformity by saying, let us assume soil is sugar.
Yeah, it's a really weird instruction. The text is trying to ask the student to imagine a hypothetical, but the metaphor is just clumsy.
Aram jumps all over it. He writes, let us assume soil is sugar, which it is not, by the way. The top sips will be more sweet and the bottom less. He's rightfully confused. If soil were sugar, it would dissolve. Since it's soil, it makes the bottom gritty, not sweet.
He is offended by the logic of the analogy, but he gives us a much better example of a heterogeneous mixture later on. Chocolate chip cookies.
Yum, he adds. Just another typo-free addition from our boy Aram.
And it's a perfect example. You have the dough and you have the chips. They aren't mixed evenly. One bite might have 3 chicks, the next bite might have 0. That is true heterogeneity. You can mechanically separate them with a toothpick if you wanted to.
Okay, so we know what things are made of. Now we get to the action movie part of the deep dive. Section 3, the toolkit of separation. Why do we even need to separate things?
Civilization is basically built on separation. We separate metal from rock to make tools. We separate grain from husk to make food. We separate medicine from poisonous plants. It's all about isolating the variable you want.
The text lists a bunch of methods for separating solids, and some of these feel very ancient, very agricultural.
They are. These are technologies that have sustained human civilization for thousands of years. Take handpicking, for example.
The simplest method. You see a stone in the rice, you pick it out.
It works when the impurity looks different color, different shape, and when there isn't too much of it. But think about the cognitive load. You have to scan, identify, and remove. You wouldn't handpick salt out of sand. It would take a lifetime.
Next up is threshing. This is harvest time.
Right. You have cut the wheat stalks, but you need the grain, not the stalk. Threshing is basically beating the plant up until it gives you the food.
The text mentions trampling them under the feet of animals like bullocks.
It's a violent separation. You are breaking the physical connection between the seed and the plant.
But now you have a pile of grain mixed with chaff, the husks. How do you separate those? They're about the same size. You can't really handpick them.
Enter winnowing. This is where you use the wind. And this is listed as Aram's favorite type of separation.
I can see why. The visual is great. You stand on a raised platform with a plate of this mixture, grain and husks, and you just let it slide off.
It's physics in action. Gravity pulls everything down, but the wind pushes against the falling objects.
So it's a battle between gravity and aerodynamics.
Exactly. The grain is dense and aerodynamic. It punches through the wind. Its terminal velocity is high, and its vector is mostly vertical. It falls straight down into a pile.
And the husk?
The husk is basically a parachute. High surface area, very low mass. The wind force overcomes the gravitational force easily. It doesn't just fall, it sails. So you end up with 2 separate piles, one of food, one of waste, just by using moving air.
Aram describes doing this with sand and dried leaves. He says, the sand falls straight down, the leaves blow away. It's satisfying. It's sorting without touching.
It's density separation using a fluid medium air.
Next is sieving, using a mesh.
This separates based purely on size. Small things fall through, big things stay on top. We do this with flour to get the clumps out. Construction sites do this to get stones out of sand.
And Aram has a specific application for this too, he says. Like separating sand to find big rocks to keep on my shelf.
I love that. To a construction worker, the rocks are the impurity to be removed so the sand is smooth. But to Aram, the sand is the impurity and the big, cool rocks are the treasure. Separation is subjective. It depends entirely on what you want to keep.
That's a really deep point. One person's waste is another person's collection.
Exactly.
Moving on to section 4, we are leaving the farm and entering the physics lab. The magic of magnetism.
This is a separation technique that feels like a superpower. If one component is magnetic, like iron, and the other isn't, you can just lift the iron right out.
The text suggests using a magnet to separate iron nails from sand. Practical. But Aram takes it to the next level.
He shares a story. He dropped a nail into a container full of pens and pencils. Now, he could have just dumped the cup out, but no. He writes, I picked up a neodymium magnet way too strong for my application XD and got it out.
I love the way too strong part. Neodymium magnets are those silver ones that can seriously pinch your finger if you aren't careful. You probably lifted the pens and maybe the stapler on the next desk over.
It shows the joy of overkill in science. Why do it the simple way when you can use a high-powered magnetic field?
But then the text and Aram get into something that honestly blew my mind a little bit. Finding iron in breakfast cereal.
Oh, this is a classic experiment.
Aram writes, in certain types of cereal, they have iron in it. Add water in a plastic Ziploc bag and mush it together. Bring a strong magnet near it and you can see little iron particles.
And his reaction is priceless. He says, why is it there in my food XD?
It is a valid question. When I see iron on the nutrition label, I assume it's, a vitamin, a biological molecule. I don't assume it's literally metal shavings.
But it is. It's fortification. Our bodies need iron to make hemoglobin, which carries oxygen in our blood. If we don't get enough, we get anemic. So feed companies add iron, and often they add it in the form of reduced iron, which is literally microscopic metal dust.
So when Aram sees those black specks moving towards the magnet in his Ziploc bag, he is looking at the actual metal that was supposed to go into his blood.
Correct. Your stomach acid is strong enough to dissolve that metal and turn it into iron ions that your body can absorb. It's a really visceral way to connect chemistry to biology. You are eating metal.
Aram also adds a side note, squared a note within a note.
The matchstick trick.
Yeah, he says, if you burn a matchstick, and after extinguishing it, you can rub the top part to get iron filing type things. And he adds a crucial safety tip. Make sure it's cold before rubbing it. I've learned my lesson.
Wise words from a scarred scientist. This works because the chemical composition of some match heads includes iron oxide rust basically as a coloring agent or regulator. When you strike the match, it burns. That combustion is a chemical reaction that can act as a reduction.
Reduction meaning removing oxygen.
Exactly. The heat and the carbon from the wood strip the oxygen away from the iron oxide, leaving behind tiny bits of metallic magnetic iron. So you transform a non-magnetic match head into magnetic dust just with fire.
It's alchemy.
It's chemistry.
Same difference sometimes. Okay, let's move to section 5. Separating solids from liquids. Specifically solids that don't dissolve. Insoluble ones.
So we are talking about muddy water or tea leaves in tea.
The first method is sedimentation and decantation.
Sedimentation is just letting gravity do the work.
Let the mud settle to the bottom. It requires a lot of patience.
And decantation is the art of pouring. You carefully pour off the clear water, the supernatant, without disturbing the sludge at the bottom.
It requires a steady hand, and honestly, it's rarely perfect. You always lose a little water or pour a little mud. It's a good enough method, not a precision method.
So if the particles are too small and won't settle, the text suggests loading. And this involves a substance called alum.
Alum is a coagulant. In the text, they call it fulcari. Here's the problem. Sometimes dirt particles in water are so small that they have a tiny electric charge. That charge makes them repel each other. They act like tiny magnets pushing away. Because they repel, they never clump together, so they never get heavy enough to sink. They just float forever.
So you have permanently cloudy water. Enter alum. When you dissolve alum, it neutralizes that electric charge. Suddenly, the particles stop repelling. They start bumping into each other and sticking.
And as they stick,
they get bigger and heavier. We call these flocks. And once they are heavy enough, gravity takes over and they sink rapidly. It clears the water like magic.
Aram is a big fan of this one. He writes, try this in real life.
Yeah.
A deep dive. Yes, this is a reference to you. I know who I'm talking to. It's really fun to watch.
He broke the fourth wall. He knows we are reading his notes.
Hi, Aram. We are indeed visualizing this in real life. It's fascinating that he finds the visual aspect so engaging, watching the cloudiness suddenly clump and drop.
It is satisfying. It's order emerging from chaos.
Then we have filtration. This is the coffee filter method.
This is more precise than decantation. You use a barrier filter paper cloth, a mesh that has holes small enough to let liquid through, but too small for the solid.
The solid is the residue, the liquid is the filtrate.
Simple but essential. It's how our kidneys work. Our kidneys are basically advanced biological filtration units keeping our blood clean.
Now section 6. What if the solid does dissolve? Solutions and solubility.
Now we have a problem. You can't filter salts out of water. The salt particles have broken down into individual ions. They are molecule-sized. They go right through the paper.
So we use evaporation.
We simply remove the solvent. If you heat the salt water, the water turns to gas and leaves. The salt, which has a much higher boiling point, stays behind. This is how we get sea salt.
But the text reminds us the water is lost to the air. Aram comments here. If you read this, you may be wondering, is there any way to get the water back? Well, then you should go see distillation. It will blow your mind.
He's a very good hype man for distillation. But before we get there, we have to talk about condensation.
Which is just the reverse of evaporation. Catching that steam and cooling it down until it turns back into liquid.
Right. And this leads us to the concept of solubility. We have the solid, the salt, and the solvent, the water.
And there's a limit. You mentioned this earlier with the sugar water, the saturated solution.
Right. Imagine the water molecules are like a hotel. There are only so many rooms, spaces between molecules where the salt can stay. Once the hotel is full, no more salt can dissolve. That's saturation.
And this is the cool part. You can cheat the system.
You can heat it up.
The text explains that heating the solution allows more sugar or salt to dissolve.
Thinking back to the hotel analogy, heating the water makes the molecules move faster and spread out. It's like building an extension on the hotel. Suddenly you have room for more salt.
But what happens when the hotel cools down?
The extension collapses. The water molecules get closer together again. They kick out the extra salt guests.
Aram did this experiment. He calls it the salty fridge experiment.
Walk us through it. What did he do?
He writes, I saturated it and then kept it in the fridge and saw there was a bit of salt left over at the bottom.
Perfect observation. He made a saturated solution at room temperature. When he put it in the fridge, the water cooled down. Cold water can hold less salt than warm water. So the water precipitated the excess salt. That's the salt he saw at the bottom.
He also mentions he tasted it. I did drink. It was a bit less salty than the regular one.
Aram, please stop drinking your chemistry experiments. We talked about this.
At least it was just salt water. But he admits, I didn't taste the hot one as I don't want hot and super salty water.
Smart kid. He understands thermodynamics and he has boundaries.
This brings us to section 7, separating liquids from liquids.
This depends entirely on whether the liquids like each other.
Immiscible versus miscible.
Immiscible means they don't mix. Like oil and water, they form distinct layers.
Aram has a reaction to the word oil.
He writes, America, did I hear oil?
A little geopolitical meme humor in the margins of a science text.
He's keeping it current. We're just impartially recording his marginalia here.
Just reading what's on the page. So to separate oil and water, you use a separating funnel.
It's a cone with a tap at the bottom. Since water is heavier, more dense, it sinks to the bottom. You open the tap, let the water run out, and close it exactly when the oil reaches the bottom. It's purely density-based.
But what if they do mix? Miscible liquids, like alcohol and water.
Then you can't use a funnel. They're one phase. You need Aram's mind-blowing method. Distillation.
How does it work?
It uses boiling points. Alcohol boils at around 78 degrees Celsius. Water boils at 100 degrees. So if you heat the mixture to, say, 80 degrees...
The water is just hot, but the alcohol is boiling.
Exactly. The alcohol turns to vapor and flies up. The water stays in the pot. You catch that alcohol vapor, run it through a cooling tube, a condenser, and boom, it turns back into liquid. You have pure alcohol in one cup and water in the other.
And this is how we get gasoline, right?
Yes. Crude oil is a mixture of hundreds of different hydrocarbons, chains of carbon and hydrogen of all different lengths. They all boil at completely different temperatures.
So they use fractional distillation.
Imagine a giant tower. The bottom is incredibly hot. The top is cool. You pump in crude oil and heat it. The really heavy stuff like asphalt doesn't boil. It falls to the bottom. The lighter stuff panel, diesel, kerosene, petrol, boils and rises up the tower. As they get higher, it gets cooler, so they condense at different levels. It's like sorting them by how volatile they are.
And petroleum jelly.
Yes. The thick sludge left over that isn't quite asphalt but isn't quite fuel.
Aram has a beef with Vaseline.
He does. He writes, better known as Vaseline, but like, I really don't like the name petroleum jelly. It seems like I'm putting fuel all over my face, XD.
I mean, he's not wrong. It is a byproduct of the oil industry. It is hydrocarbons.
It is purified Arum. It won't ignite on your face. But it is funny to think about smearing jelly fuel on your dry lips. It highlights how connected all these materials are. The same source, dead dinosaurs and algae from millions of years ago, gives us the fuel for our cars and the moisturizer for our skin. It's just a matter of separation.
Finally, Section 8. Water. The universal solvent.
This brings it all home. Why does any of this matter? Because water dissolves almost everything.
The text calls it the universal solvent. Why is it so good at dissolving things?
It comes down to the exact shape of the molecule. H2O looks like Mickey Mouse. The ears are hydrogen, the face is oxygen. The oxygen side is slightly negative, the hydrogen side is slightly positive.
So a magnet.
It's a polar molecule. It can grab onto positive things like sodium and negative things like chlorine and rip them apart. That's why it dissolves salt. That's why it dissolves sugar.
And biologically, this is everything.
We are basically bags of walking water mixtures. Our blood is a mixture. Our cytoplasm is a mixture. Life only exists because water is such a good solvent. It allows chemicals to meet, bump into each other, and react. If water was pure and didn't dissolve anything, life would stop. We couldn't transport nutrients. We couldn't remove waste.
We also get a quick overview of how drinking water reaches our taps. It uses all the methods we discussed.
It does. You take river water, then sedimentation to let the big stuff sink, then loading where you add alum to sink the small stuff, then filtration, usually sand filters, and finally chlorination to kill the bugs.
It's a giant industrial version of RM's kitchen experiments.
Exactly.
So we have traveled from the rigid definition of a pure element to the complex industrial refining of crude oil.
We have covered a lot of ground.
What's the big takeaway for you from all this source material?
I think it's this: the world presents itself to us as a messy, jumbled mixture. Nature is chaotic. Chemistry, specifically separation chemistry, is the human attempt to create order from that chaos. We want the iron without the rock. We want the water without the mud. We want the sugar without the cane. Civilization is built entirely on the ability to separate.
And for me, the takeaway is the ARM factor.
The ARM factor, I like that.
Science can feel distant, boring sometimes. But ARM reminds us that science is something you actively do. It's tasting the less salty water, even if you probably shouldn't. It's marveling at the strength of a magnet. It's questioning why a moisturizer is named after petrol.
It's about being an active participant in the physical world, not just a passive observer reading a book.
Precisely. And ignoring the typos along the way.
Naturally. I have a final thought for you listeners to mull over.
Let's hear it.
We spent this whole hour talking about how to separate things, how to get to purity. But I want you to consider this water is the universal solvent. It wants to mix. A pure substance is actually a high-energy, unstable state in the context of the environment. Iron wants to rust and mix with oxygen. Water wants to dissolve salts.
Right.
So is purity actually unnatural? Is the mixture the natural resting state of the universe? And if so, when we strive for purity in our materials, our food, our environment, are we fighting a losing battle against the fundamental nature of matter?
Wow, that is a lot to think about next time I filter my morning coffee.
Just don't drink the distilled water.
We definitely won't. Thanks for listening to this deep dive. And Aram, if you're out there listening, keep experimenting. But maybe lay off the matchsticks for a little while.
Safety first.
See y'all next time.